Dear friends, we are here again, and I think this is our sixth webinar meeting of our colloquium portable X-ray fluorescence that is organized by the European Academy of Science and Arts, STEMAC expert group, and the global pXRF network. For our academy, this is a follow-up of a specialized section of the successful colloquia Arts Meet Science and the further activity of STEM in Arts and Culture, STEMAC expert group. Myself and Michaela wish to express our gratitude to Keelie Rix always and Doris Klida for their immense technical help in organizing this colloquia. Today we have two important speakers, Dr. Anno Hein and Dr. Liritzis. I would pass on the online podium to Michaela to introduce the first speaker and start with the first presentation. Michaela.
Thank you. I'm very honored to introduce Liritzis, who holds not only a PhD in anthropology from the University of New Mexico, but also a Bachelor of Science in biology, which I didn't know until today. So that's impressive. Many of us working in pXRF know him from his work as a senior applications scientist for Bruker, where he was traveling the world and visiting a lot of different labs and helping us out with our pXRF problems. He now has his own company, Decision Tree LLC, which offers rapid advanced analytics to make use of the volumes of data provided by scientific instruments. He also hosts for a couple of years now a very, very important website for all of us, which is called XRF Guru, where you can find different kinds of workshops and information, especially in working with spectra, but also how to understand pXRF data. He is also very involved in the global pXRF network, which we started now a year ago, where we try to bring together the pXRF community, and also this colloquium is part of what we do in the network and what he helps to do. He's still active in science, so he still publishes. He also is involved in a lot of research projects and presents in a variety of contexts, also conducts workshops and collaborates with, I think, many of us. Today, he's gonna talk about another field he's getting more and more involved now, which is about AI in XRF studies. And with that, Lee, I would hand the floor over to you.
All right, and see if I can share my screen here. Thank you for the very kind introduction. And can everyone see it?
Yes, yes.
Excellent. All right, we'll proceed. Well, thank you all for coming in. Early morning for me, late evening for you, mostly, I'm guessing. What I want to start with in talking about XRF and AI applications is to kind of ground us into thinking about it along two primary axes. The first axis, running from left to right, is from quantitative to qualitative. And this is quite familiar to us, I think, if you've engaged in the humanities or in anthropology, which is our question answered by quantitative data or by qualitative understanding of what we're working with? So an example of this, I think very familiar to folks in XRF, is calibration. A calibration is where we try to translate the spectrum into quantitative numbers. So that'd be a great example of quantitative analysis. But of course, many of us use XRF to identify potential sources for objects. In this case, the sources we're trying to understand are actually more qualitative concepts, since the people who would have engaged with those sources would have been working with, you know, this region or this mountain, a more qualitative understanding of their world. Now, with AI, there's another axis we must consider in addition to our own questions, and that is the nature of the data. Now, the data can be either structured or unstructured. Now, I want to take a moment to highlight what these mean. The simplest way, not a complete understanding, but the simplest way to understand this is, can you represent this in a spreadsheet or not, right? So in the case of chemical concentrations from a pXRF, let's say I scanned, this rock, this piece of obsidian, and I have rubidium, strontium, yttrium, zirconium, and niobium. That can fit in a spreadsheet. So that is structured data. Contrast this with another AI application, say ChatGPT, where you ask it a question and it provides an answer. Could you put your question in a spreadsheet? Not really. That's unstructured data. Another example might be facial algorithms in an image. Is that structured data? Not really. The face can be anywhere. So with AI, the nature of that data becomes a little different. In this case, for our purposes, we're going to treat spectrum as unstructured data for a couple reasons. The first is that each instrument has a slightly different spectrum. And second, we often include other data besides just the spectrum to understand and conceptualize that. But those are our primary axes. Now, with that, I want to zoom out a little bit and think about the type of questions we're asking. So, a question type for quantitative analysis might be, what is the percent of loss on ignition for a given sample, right? Now, I want to highlight loss on ignition because we don't have an elemental line in the XRF for it, right? When we point the XRF, we're getting elemental readouts of that material. But I found, both working with data, a number of different environments, that one of the most interesting things you can do reliably with machine learning and XRF data is identify loss or predict loss on ignition. Now, for those who don't know, loss on ignition is where I take a clay object or a geologic material really more broadly, I put it in an oven, and I basically bake off all the water weight and CO2. So if I have a lot of calcium carbonate, I can degas it with high enough heat to calcium oxide, and then I can measure the object after that heat treatment, and there's going to be a difference in mass. And that mass difference is the loss on ignition, the mass lost through the heating process. Another example of a question is, and I'll need to just realize I need to minimize this here. Let's see if I can find it. Just a minute. Let's minimize that and let's resume. Another example is our question type. Does sample A belong to group Z? It might be an example of a qualitative group. That's a provenance question. Now, on our structured axis of going from top down, we've got model types. Typically speaking, for running a machine learning algorithm on structured data, you don't want to do a neural network usually. My favorite phrase in the AI community is that using a neural network on spreadsheet data is like wearing socks with sandals. Like, it just doesn't work. You're kind of defeating the purpose. So in this case, we want to use simpler model types, such as gradient boosting or forests, random forests in particular. For unstructured data, neural networks are basically all you have available to you because most other algorithms assume a structured data type. Now, a neural network is basically, you can think about it as a mental model of your brain, but in place of a neuron, put a numeric weight where each neuron goes. And then there's different ways to activate those neurons. And because they're densely interconnected in all these different ways, we then see all we can then basically have the model store a memory of how those things relate. So the next thing I want to mention, though, is that AI isn't some magic black box. It is just statistics. And so for statistics, we're going to have this nice white circle that represents, the white light, that everything is included within it. Now, within that, with statistics, actually, let's hop back just a minute. Statistics, when you think about it, the most simple example of statistics are, I have these data, I measured the heights of these individuals, and I found that there's a significant difference between group A and group B. P is minus 0.05. Well, the idea with our next level of machine learning is, if we know that we've got a criterion for distinguishing these two groups, could we then ask the machine to evaluate every possibility until we get a p-value that matches what we want? In the sciences, this is a common problem known as p-hacking, where you just do whatever you can to get that p-value to an acceptable publishing layer. Machine learning takes that a step further, saying, look, if we make this robust, we can design a generic algorithm that can always find the difference. And that would be an example of machine learning. So in this case, rather than stopping at, I ran this one trial and this is my result, we basically chain everything together so the statistics learn themselves, and that's machine learning. Within machine learning is a subcategory called deep learning. This is with neural networks, typically deeper than seven interconnected layers. And these are the models that have caused the revolution since 2012, I think, with the AlexNet paper that successfully recognized faces extremely well, or image classification. And these deep learning methods are interesting because the brain can be stored and relearned, allowing transfer learning. So at this point, we start getting models that are not quite future-proof, but can be integrated in the future. Now, within deep learning, starting in about 2018, we have transformers with the publication of Attention is All You Need. What this paper found is that having attention heads within a neural network can both speed up processing, speed up inference, but also allow greater capability to learn new material. So these networks are truly transformative. This is the core thing that allowed for the development of generative AI, which is the thing we're currently wrestling with today. Things like ChatGPT, or image generation software, or video deepfake software. This is where basically you can take text and translate it to whatever you want through the just raw power of statistical association. But the thing I want to really stress is that all of this is just for smaller and smaller subdivisions of statistics. My favorite webcomic demonstrates this, is that like basically just how you describe what you're doing changes how people perceive it entirely. But really, when we get down to it, what we call artificial intelligence or AI is just a subcategory of statistics. So if we really want to understand what AI is, we need to understand what statistics are. So to do that, let's ask ChatGPT. So here I asked ChatGPT, I need to make a presentation and do a single bullet point on what statistics are. And ChatGPT told me statistics formalize uncertainty by quantifying how likely outcomes are using probability models to make inferences from incomplete or noisy data. The thing I want to highlight here is we've got kind of a circular problem, right? If AI is a part of statistics, why is AI answering what it is? Well, if we go further, how did it even create this answer? And I asked it to create an image to demonstrate how it learned. And here's a rough diagram of how it works. You'll notice here the words are all interconnected to each other. Basically, the way a model like ChatGPT learns is by giving each word a number. So for example, statistics might be 1, formalize might be 7, uncertainty might be 353, by might be 2, etc. And then it maps those out to create a statistical probability of what the right answer should be with the right training data. So it's just statistics at the end of the day, even though if interpreted through our social brains, it seems almost magical. Statistics is the evaluation of uncertainty through quantitative means. LLMs just extend that process using tokenization, or basically ascribing numbers to words to make those associations. And then the key network is just when you get a big enough network with billions of neurons that crosses the boundary to where it provides very useful information. So in simplest terms, let's just really boil it down. When there's more than one thing, there tends to be variance in that one thing. That can be the height of people, the chemical composition of ceramic shards, the volcanic trace elements left behind by a volcano eruption. And that variance tends to be predictable. We can represent an average to represent the whole, in this case a mean, though it could also be median or mode. We add a statement of variance around that average, the standard deviation, and then from that, we create a model of our expectations. And everything proceeds from that. No matter how complicated the AI is, if you boil it down, this is the representation it is working from. So going back to our XRF alignment chart, I organized 4 case studies to look at for each of these, for structured quantitative, structured qualitative, unstructured qualitative, and finally unstructured quantitative. To start, let's work with calibration, which is something every pXRF user has had to engage with at some point in their work. Now here, I'm using a small test kit developed by the IRN pXRF Ceramic Users Group Network. This is based on funding from the Centre d'études Alexandrine. It has worked with a number of partners, including the Fitch Laboratory in Athens, which has provided wavelength dispersive XRF. Now, what I've done here is I have created a model for loss on ignition from data from one Vanta instrument. Now, just to guide you on this bivariate plot, on the y-axis is loss on ignition, which is the number we know, and then loss on ignition, which is the estimate from the machine learning model the XRF produced. As you can see, it did very well with an R squared of 0.99999 and a slope of 1. The dotted line you see in the background here is the perfect 0 to 1 relationship. If you really look closely, we're not quite perfect. There's a little bit of an offset that becomes very apparent by about 3%, where our model would slightly overestimate the loss on ignition compared to the known value. The way I came about this was using an XGBoost linear model. So this would be an example of gradient boosting. Gradient boosting comes from this idea that the best model is the sum of the weakest models. So basically, you get a model to find every possible way to be wrong. And when you understand its wrongness completely through weak learnability, that can teach us more about the real relationships. So with XGBoost Linear, it ran for about 275 iterations through 1,436 boosting rounds. And then I did a random grid search to find out the right parameters. The parameters tested were learning rate, which is known as eta, L1 normalization, which is ridge regression, that's alpha, and then L2, which is lasso. And then these values were basically determined through brute force by modeling all the alternatives, and that is the resulting model. Now, you look at this, you wonder, how did it come up with this? How do we get something like loss on ignition, which again requires destructive analysis? You have to bake off that carbon and that CO2 and water fraction. How do we get that with XRF? Well, we can understand more about that by then asking the machine learning algorithm, hey, how do you weight these variables? And what we find right off the bat is that our best predictor is calcium. Why would calcium be such a good predictor? Well, if you think about it, if we've got a large CaCO3 component to these ceramics, the CO2 is mostly coming from that CaCO3, so it's basically learning using calcium to estimate LOI, which makes good sense. That's probably what we're physically seeing. Manganese is the next most significant predictor, which also makes sense because manganese is primarily formed via manganese oxide precipitation in oxic waters, which is necessary to form calcium carbonate in these paleo environments. So when we actually look at the model, what it's doing is it's using what a geologist would call our formation environment to extrapolate these properties. And this is quite powerful. It isn't just loss on ignition you can reconstruct with this. And some of these findings become relevant to understanding source, which we'll discuss in the very near future. So that is calibration in a nutshell and how we can use AI. The key point is even though the algorithms are quite complex, with the right understanding of geology, we can understand how it came to its conclusion. The other key thing is this is an empirical calibration method, so our results are only as universal as our data. So in this case, it's just those 18 standards. If we add more standards, this model may not be as predictive, or crucially, add new clay deposits for the formation environment. In any case, that's an example of structured quantitative data. Let's now look at structured qualitative data for provenance. Now this one, I have been begging my co-authors to finally let me share some of these results. We've been working on this for almost a decade now. What we're doing is we're doing clay sourcing on Mesopotamian cuneiform tablets, specifically from the Ur-3 period in summer, so about 21st century BC. Now, the problem isn't just archaeological. Obviously, we want to learn more about these clays and where they come from, but it's also law enforcement. A lot of the tablet trade has been connected to terror groups like ISIS that use this to subsidize their activities. So understanding where these tablets come from isn't just a matter of restoring provenance and scientific value to them, but also trying to address these networks of looting that support a lot of other activities that are dangerous for folks. So we've gotten funding from a number of different sources to explore ways to do this. Now, just to review the area, we're looking at a small group of tells that were active in the Ur-3 period, in specifically Tel Asmar, Kafja, Nippur, Adab. We don't have as many excavated from Uruk, unfortunately. Those are our art market sample, but that's just a small sample. Now, the model we used to interrogate this, we went through a lot of different variations of it. And the one that I found worked best kind of violates my rule a little bit on what model to use, but it is a transformer network. So this is the same basic type of model as exists with ChatGPT. So I call this the GeoChem CLS model. Now, what I like about this model is we incorporate the element itself. So we're tokenizing the element name before quantifying. Most gradient boosting methods will just kind of look at the order of columns on the spreadsheet. Here, we're actually incorporating the geologic knowledge into that neural network. Now, we ran this network through, it had about 400,000 parameters. And then the way we trained it is, I think Anna will describe this method a little more. It sounds like we've independently come to the same conclusion. But here, for each element, we've got a normal distribution for each element's concentrations in each site. So in this case, Edab, Ishali, Kafja, Nippur, Nuzi, and then finally Tel Asmar. So for training the model, one of the problems I ran into is I would run into overfitting very quickly. Overfitting is where the AI just memorizes the training data so that it's very good for the data it's seen, but it cannot generalize to new contexts. So in this case, using these probability distributions, I synthesize data every single iteration. So we're manufacturing new tablets that are within each. And then using this method, after about 4 hours of training, we used a voting method. So we measured each tablet multiple times, and then we basically counted up which site was the majority of observations. So for our test data set, or our validation data set, I should say, which was completely removed from all training, completely blind, we actually have an accuracy rate total of about 89% for all observations. But when we actually take each tablet and look at each individual analysis, we find that we would have not missed a single one. We would have had a perfect attribution of each of these to their original site of excavation. So this was great. What's really good about this model, and one of my complaints about most sourcing methods, is we don't really define unknown. So in a second variant of the model, we take all the white space here you see for rubidium, for strontium, for yttrium, and we model unknowns and train it to recognize unknowns that are unobserved. So that way the model can also say, I just don't know based on the chemical distribution. There is a compromise on that. We say our accuracy rate dropped down to about 93%. But we've also got this new power, which is the ability for the AI to say, I don't know, this one needs further research. But that is an example of provenance studies using structured data. Now we get to unstructured data, which is more complicated. I won't dwell on this too much, but one example would be inter-instrumental corrections. Now, for this study, I took 450 XRF instruments that measured the same 200 standards, and I attempted to use a reticulated transformer network to memorize the variation and see if we could predict. So the idea being that if I have 450 instruments, I can pick one to be the master, and the goal of the network is to translate spectrum from one to spectrum to another. Now, why would we need to do this? Well, each instrument has different components inside. The tube might be more or less powerful. The anode might be a little different. The cathode might run a little hotter. There might be variation in how thick the graphene window is on the detector. A number of things. This is why you have to calibrate each unit individually. The idea here is can we use a machine learning approach to bulk force identify that? So here's an example. Green here is my first instrument, and orange is my second or target instrument. And then blue is my process second instrument. So the blue spectrum should match the green one. We expect the orange one to be different, but the blue one basically forces the second to match the first. Now, this took days to train, and to be honest, I'm not happy with these results, and I don't think this is the right approach, but I want to show you sort of this first draft. The first one here is it works. You see that my second instrument had a higher chromium peak right here than the green, but the blue matches so perfectly you can't even see it. So in this case, we fixed the fact that the second instrument was more receptive to chromium. You can see here for our nickel K beta that everything worked just fine. But you also see over here for our molybdenum, it didn't work so well. We see that the blue has actually added more error than already existed with the orange. And this is actually one of the better spectrum to come out from this result. So my interpretation is that this method won't work on the spectral level, unfortunately, or at least not with the model architectures we have today. But that's important. We don't always get, the outcomes we want for. AI isn't a magic box. Sometimes it just doesn't work for the problem. but this is an example of how to use it on unstructured XRF data. And then lastly, let's take a look at unstructured data using species identification. Now, this is from a publication Aaron Sugar and Gary Kelly and I did a few years ago, where we looked at XRF scans of multiple pieces of wood. And the idea was, could we infer species of the wood using XRF data? Now, as you can see here, to the human eye, we could see this. We could build a photo method to do this quite easily. But the idea being that if I have an XRF scan of a cultural heritage object, or let's say a mask used by a mask or a support beam in a structure, I might not be able to get this information, but the XRF spectrum I'll have readily available. So we basically scanned each of these pieces of wood about 360 times each and built our data set accordingly. We used a one-dimensional convolutional neural network. This is basically the same type of neural network used for facial recognition in, like, let's say your Facebook photos, but instead it's one-dimensional to fit in a spectrum. So we're trying to use dimensional representations of an XRF spectrum in the same way we'd use for photo classification. Now, what we found is that the model performed with 100% accuracy. It just worked miraculously well. Here's an example of its training with accuracy, and you can see that once we hit about 500 epochs, our validation and training data are just perfect. We do see big jumps in validation data, but it settles by the end to merge and give us a good result. But what was really confusing to us is we did the importance spectrum. Now, this basically weights the entire spectrum on what's important. What features is this neural network using to identify, what species of wood? And we still don't have an answer for this. All the spectrum below 2 keV, that is all it was using to identify species of wood. There was almost no importance to spectrum down the line. We still don't understand this result. Is it an artifact of how it's processing the spectrum? Or is there really information at the very start of the spectrum by silicon that informs it of wood? We don't know. Outstanding, but we do know it worked exceptionally well, much better than we had anticipated. So that is our 4 axes. Once again, we've shown examples from different question types, such as quantitative questions and qualitative questions, but also model structures that range from structured gradient boosting to transformer networks for unstructured data. Now, the key thing I want you to take away from these case studies is the first is the model type. The utility of the model is oriented around the type of data you're putting in. The first thing, if you don't know how to answer this question, the answer is probably structured models, what you want to look at. But my rule of thumb is if you can fit it in a spreadsheet, use gradient boosting or random forests. If it doesn't fit in a spreadsheet, if there's no way to represent this using an X and a Y axis, then look at neural networks. And then, of course, question types, which is, I think no one here needs a reminder that your question guides the method. And that's really the way it should be. The worst is that we can only ask certain questions because our methods only support those questions. That's not acceptable. So really think about your question and then try to aim for that. With that, would love to thank all the collaborators I've worked with over the years who've helped me refine and help these methods. Particular shout outs to everyone in the IRN pXRF ceramic users group, everyone at the University of Chicago and Cambridge helping with the cuneiform tablet project, and then lastly, Queen's University and the Canadian government for providing data for the wood study. And with that, I think it is now Anno's turn.
Michaela.
Thank you very much. I think it's now up to you, Ioannis, to introduce Anno.
Yes, so the questions will be at the end for both the speakers.
Yes.
Okay. So our next speaker is Anno Hein, speaking on machine learning approaches in the evaluation of pXRF data and provenance studies of transport amphorae. Dr. Anno Hein is senior researcher at the Institute for Nanoscience and Nanotechnology, National Research Center Demokritos in Athens. He has studied physics and informatics at the University of Bonn with a diploma thesis about the neutral activation analysis of archaeological ceramics and a PhD about total reflection X-ray fluorescence with synchrotron radiation at the Bone Electron Stretcher Accelerator, which he finalized in 1996. After working in various projects concerning the characterization and conservation of archaeological materials in Greece, he took a permanent position as senior researcher in the Cultural Heritage Program at the National Center for Physical Research in Demokritos in 2010. His research interest in the field of cultural heritage concerned the investigation of archaeological materials in view of raw material management, manufacturing processes, dissemination, and technology transfer. He has a particular interest in studies of the design and thermomechanical performance of functional ceramics and built structures. This involves, apart from material testing, the development of digital multi-scale models, which can be evaluated, for example, in computer simulations, and with the finite element method or computational fluid dynamics. Furthermore, he works on data management in view of open source database development and the evaluation of big data collected in the physicochemical characterization of archaeological materials and raw materials. For this, apart from traditional multivariate statistics, he is also applying methods for automatic pattern recognition and machine learning. He is teaching in master courses at two Greek universities, and he has given invited guest lectures at several European universities and also supervising PhD students. Dear Anno, the podium is yours.
Thank you, Ioannis. I will try to share my screen now. This is one second.
We can see your presentation.
You can
So
see
the
my
whole one.
So this works. Thank you for the introduction. Thank you for the.
Anno, we don't see just the first slide. We see the whole presentation with all your slides on the side.
Oh, good. Wait 1 second. How do I do this? Wait 1 second.
If you just share the
can do it.
screen and then start the presentation, it should be full screen.
Share the screen. Share. Do you see now the presentation or the slides?
We see the presentation with the slides on the side. So if you just start the presentation, we should only see.
Wait. Sorry.
No worries. It's acting up. Like the beamer in Alexandria.
Wait. So it's the same.
You can do it.
Yes. Don't worry. Don't worry. Share. Now I have. And
Yeah, another possibility, if you have two monitors, that might be reading the other screen.
no, it doesn't. Normally it works that I share my PowerPoint and then go into the presentation mode.
Yes.
But it doesn't work.
It doesn't work. Okay, you can.
Does it work now? Do you see my presentation or my?
You can see. We can see the presentation, but not the total with the slides. But that's better. If you can just go on.
No. Wait. You don't see my presentation. You see my PowerPoint.
Yeah, we see the screen with your PowerPoint. So if you have two screens, when you start the screen sharing, you can pick the other screen And when you start the presentation, then we see only the presentation. Yeah,
Yes.
now we just see the first slide.
Okay.
Well done.
Okay, thank you, thank you. Sorry for the delay. So
That's okay. Don't worry.
this is now more about an application of machine learning.
Yeah.
So I will not give you now all this background about structured, unstructured, quantitative, qualitative data. Machine learning approaches, evaluation of pXRF data and provenance studies of transport amphorae. So what is the scope of an archaeological ceramic study? When we are looking at ceramics, we don't look at singular objects or unique objects, but we are looking at representatives of categories with specific attributes. So the scope is to define the categories and to categorize the cases. This we try in the view of looking at the organization of manufacture when we are looking at manufacturing centers, or when we are looking at trading centers or consumption centers, we're looking at trade networks. So amphoras, it's a specific case now of ceramic studies, because amphoras, they were not traded because they were nice ceramic vessels, but they were traded as containers. They were the standard containers for marine transport of liquid and solid goods. So when we are looking at trade networks of on the basis of amphoras, we are investigating the trade networks for wine, oil, fish sauce, or something else. I was speaking about categories, ceramic categories. We define categories according to different criteria, such in this present case as elemental composition, but it can be also petrographic fabric, so images, mineralogic composition, micromorphology, material properties, vessel type, chronology, so more the archaeological criteria, decoration, inscription, stamps. Stamps is also very interesting for amphoras. Then the origin of manufacture can be a criterion for categorization. It's actually the criterion what we are looking at. And then the finding site is also a criterion. What is now important to look at these criteria is that if we find now two cases in the same category according to one criterion, it's not automatically that they are in the same category according to another criterion. This is what we usually get from an elemental study, an elemental analysis. This is a spreadsheet. I think it's this Newton activation analysis. And this would be a spreadsheet from portable XRF analysis. So what we have spreadsheets, what Lee already said, it's some kind of matrix where the rows are the instances, the samples, the cases, and the columns are the number of features. In this, or as the features, in this case, the elements, where we are measuring the concentrations. The scope of compositional analysis is a categorization to recognize similar cases and distinguish dissimilar cases. For this, there are conventional statistical analysis, which we know, you can distinguish exploratory data analysis, for example, what we know is principal component analysis or hierarchical cluster analysis. On the other hand, we have model-based data analysis, where we have models for the elemental composition, which are the average values, but it's also the variation of the average values. So this can be log normalized or log normal distributions. So for the data acquisition, measuring now the elemental composition, we have first to select the analytical method. We have laboratory methods where we can measure large element suits, so a lot of different elemental concentrations, and we have high precision and high accuracy. But one disadvantage is that for these laboratory methods, sampling is necessary. So we take a sample, we have to take a sample which is then measured like here in a research reactor activated with newtons for being measured the gamma radiation and for Newton activation analysis. So, and in the case of cultural heritage objects, this is a disadvantage because it's destructive. On the other hand, we have non-destructive portal methods, like in our case, what we are interested in is a portal pXRF, which is non-invasive. We also get prompt results, and we have a high number of samples, which we can potentially measure in comparably short times. The disadvantage is the mediocre, I call it mediocre, the analytical performance. We measure less elements, and we have higher analytical uncertainties, a higher variation, a higher, a lower precision, a lower repeatability of the measurements. And also the accuracy, we have a lower accuracy, so which makes problems with the calibration. If we look now at the compositional variation, we can look at the so-called covariance matrix, where we have now n elements, and we look at the standard deviations and at the covariances between the elements. The interesting thing is that we theoretically can take this covariance matrix in different parts, which is a natural true variance, which depends on the original raw materials, on the clay-paste preparation, on sliding and possible alteration of the ceramics after the deposition, after the use. Then we have variance due to sample selection, I think. This in this case, portal pXRF has the advantage that we can measure as many samples as we like. But then at last we have the contribution of the analytical variance. So we have a higher variance or higher variation of the portal pXRF data, which then affects the covariance or the overall variance. I will present you now some results of a case study which we did some years ago in Cyprus, in Paphos, at the Hellenistic Agora of Paphos. And we started, or the archaeologists started with a macroscopic categorization, with a classification of the amphora shapes, with a macroscopic identification of fabrics, and also with identification of specific stumps. Then we started with portal pXRF of a lot of samples. We use a Niton p-XRF, we use normally the soil calibration. And some of the samples were also then analyzed with Newton activation analysis and petrography. And this is the article published in 4 years ago, yes. But supportably XRF, and we use it, we use it in a kind of integrated approach, that we use it as an initial, some kind of analytical survey, and then to decide based on this initial classification, categorization, which samples we select for laboratory analysis. This was the original idea. And this is how it looks like now, this 368 data measurements of about 300 fragments. And this is a classical hierarchical clustering, and where we then try to find clusters which make sense, which we also compare them with an archaeological classification. This is how we started then 7 years ago. And normally for hierarchical clustering, we use normalized data, log ratio normalized data. And in this clustering is average linkage and Euclidean distance. This would be now a principal component analysis of the same data, which looks a little bit chaotic here. And we can try to indicate at least the different categories. But you see, you don't really, you cannot really distinguish the categories in this principal component analysis in the first two components. So the principal component analysis is a classical method for reducing the dimensions of the data. In this case, we have about 17, 18 different elemental concentrations. And with the principal component analysis, we find the first, in this case, these are the first two components which are distinguishing somehow the data. But it does not look very convincing. In this data set now, we had supposedly local ceramics, locally produced amphoras, mainly from Paphos and from Kurion, and also some which are supposedly Cypriot, but where we did not know the exact provenance. And yes, always, or we measured also some roof tiles, which we thought there would be an example of locally produced ceramics, but at the end they did not have anything to do with the ceramics. Looking at it in this classical hierarchical clustering. This would be now the imported ceramics, or the part of the assemblage which was supposed imported. And here we find some groups or some clearer clusters, which some of them we also could identify then based on specific stamps found on handles. And there were some Cohen-type amphoras, but or specifically for COS. We have also some reference portable XRF data. And these would be, in this case, all these COS samples, which you see here, where we know the provenance, because all these samples from COS have been analyzed with Newton activation analysis, and we could make a clear categorization. So this is now a mixed data set where we put the cone type amphora from Paphos and the reference data from COS. And this would be now based on 14 elements. And this is again a hierarchical cluster analysis on the log ratio transformed data. And we have these known clusters, which we know from our study on the cone amphora. And here you see really some of the Paphos which go together with the portable XRF data of samples of cone fragments where we know the provenance. And this is actually some kind of supervised pattern recognition. So we have reference data where we know the provenance, and we make classical conventional statistics and compare this mixed data set. Okay. Yes, these are the Path examples. But then we thought about, well, what is about machine learning? Can we try to do? Can machine learning help us with the clustering? The traditional programming, or the traditional statistics is we have the data, of course, we have then the rules, and with a traditional programming, in this case, I took this from TensorFlow, we get the answers. In the case of machine learning, we have the data, we put the answers, we put the predefined categories, and we produce a model which gives us the rules for classifying, for predicting the right categories. And an artificial neural network would be input layers, output layers. So we put the data in. In our case, these are element concentrations, and we get output layer categories. And in between, there might be some hidden layers, which then are connected via these connections. And as you know, these artificial neural networks, they are somehow at least how can I say it? It is an artificial model of our brain. So the neurons, and which are connected then via synapses. And we started actually with non-supervised machine learning, so with self-organizing maps, which is a specific case of artificial neural networks, and with no hidden layers, where we have only one input layer and only one output layer. So, and this would be now the hyperdimensional space. In this case, it's three-dimensional, but as I said before, when we are speaking about 16 or 18 elements, we have an 18-dimensional space, which then is projected with the self-organizing map on a two-dimensional map, which then we can define areas which then correspond to specific categories. And the data are projected on the map. And this was for this we used an implementation of this coordinate model in R. And this actually what came out then. This is a self-organized. This is a map the resulting map. It's a 10 times 10 map, toroidal. And here you see the samples or the sample composition projected on the map. And then really we could identify the areas. And it looked like that as a map gave us some kind of automatic clustering. And this would be the clusters according to the clustering that I showed you before. And this would be then the areas on the map. This is a heat map, yes. The problem was that with a random initialization of the self-organizing maps, we could not really reproduce all the time the results. So we used a series of SOMs, and then we tried to find the samples which were always in the same categories, or which were together in the same categories. And this was published actually last year, yes. And this now is a comparison of these combined self-organizing maps with the initial clusters. And where you have here, the new clusters from the self-organizing map, and where we actually see then that there is a subdivision of the clusters that we saw from the conventional clustering. And what was very interesting that when we then compared it with the NAA clusters, so with a more precise analysis, we got came to a level of subdivision of the data, of subclustering of the data, which corresponded actually to the level of the Newton activation analysis. So this was what we did with unsupervised machine learning, which gave us the impression that there's more in the data that we can see with conventional statistical analysis. And then we started supervised machine learning. Again, we based it on we predefined categories based on analysis of the same fragments with Newton activation analysis. And this would be now 33 categories. The first categories are amphoras from course. This is an older study. These are 7 clusters, and we have 7 clusters from roads. Actually, these are 6 from roads and 1 which is probably from Knidos. And then we have a couple of probably Aegean categories. And we have one, I think in the initial clustering that I showed you, it was North Africa, but it came out at the end, it was Sicily, so Western Mediterranean category. And then we have the local Cypriot categories. And from this training data, so these are portable pXRF data of samples which were also analyzed with Newton activation analysis. We put together some training data sets, and with one training data set with 7 predefined categories from course, one data set with 23 predefined categories, probably related to the Aegean region. and then 33 predefined categories which correspond to all these ceramics that found in Cyprus. And for the training, we did this classical division, 70% training for training the model, and then 30% for testing the model. We tested the model also with non-categorized data. And for this, we have two data sets. One data set with a this goes from archaic to Roman amphoras, and also from some cone amphoras found at other places, and also some clays. And then we have this data set from Paphos with, in this case, 370 pXRF analysis of about 300 amphora fragments. And these are all Hellenistic amphora fragments. So the models, okay, I copied these picture images from these site Geeks for Geeks, just for illustration. I did not have the time to make my own illustrations for this. Is a support vector machine model where we where data are divided by so-called decision planes, and this is again a two-dimensional case where we have categories, a red category, a green category, and an optimum decision plane is searched for dividing then these two categories. And the support vectors are actually then the cases which are closest to this decision plane. And in this case, it's a linear decision plane, but we can also have non-linear decision planes. And okay, these are very simple examples. Of course, it's 2 dimensions, 2 categories, but we have now 16 dimensions and 33 categories. The other model which we tried was a random forest. So everybody knows about decision trees, a single decision tree, but if we put decision trees with different criteria together, we get this kind of random forest. And also this was, which is actually a quite suitable method for small data sets, for small data sets. And for the preparation of the data, so we have this is a soil method. It's we use 1 or 2 minutes measurements, and for the data that we were looking at, or that we are looking at now, we look at 16 element concentrations, which we then use simply as features for the categorization. And some of the element concentration were below the limit of detection, where we simply put the minimum value. And the data were then normalized with centered log ratio transformation. And these are actually the first results for accuracy, precision, and recall for the models that we tested. These were the support vector machines with a linear, polynomial, and radial kernel, and then random forest with normalized data, so this normalization, and with the raw data, because you can use a random forest also with raw data. And the first table is the accuracy for this for the first case where we have only 7 categories, the training data set is 7 categories, where we see that especially the polynomial, radial, and also the normalized random forest, they have a perfect accuracy, precision, recall. And this would be then when we look at the gene amphora categories, where we have 23 categories. And this would then accuracy, precision, recall for the 33 categories. How does it look like now in the heat map? This is, you don't see it, of course. It's a heat maps with a predefined categories, and then this would be the case of support vector machine, of one support vector machine with 5 polynomial with a 5-factor polynomial kernel, and this is the random forest. And you see what does it mean, that 100% accuracy. And here this would be the data sets with the training data sets with a gene amphoras, where we see that the accuracy for the random forest is a little bit it's not as good as with the support vector machine model, and the same is now with 33 categories. This is now the comparison between the support vector machine and the random forest for the cone, for this cone amphora testing set that I showed you before, where we then have a little disagreement of the category A and the category D. And this would be now when we put this cone amphora set into the models for with all these gene categories, and what we expect, or what came out, that most of the cone amphoras or most of the fragments from this cone amphora data set is actually can be categorized as cone. And this is now, this would be that the Paphos data set again categorized with a random with a support vector machine, the random forest. What is now about deep learning, use of neural networks, artificial neural networks? For this, we need big data, a lot of data. What we have at the moment, we have about 2,200 data sets, portable XRF analysis of amphora fragments, which were taken measuring about 1,400 individual amphora samples. These are a lot of samples, a lot of measurements, but it's not enough for going now for neural networks. For this, we tried to work with synthetic data, so model data based either on the average composition and standard deviation of the compositional categories, on the random mixtures of cases from the categories, or on the covariance matrices of the training categories. This is how it looks like now. We have the original data. These are the 3 categories of these cone amphoras which have comparably a lot of samples, or the most samples. So cone A, cos A is this blue one, cos B is a green one, cos D2 is a red one. And based on these categories, based on these original data, we tried now to generate synthetic data, which is here now with a random mixture. So taking random mixtures from this green data, random mixtures from blue data, and random mixtures from the red data points. This, by the way, is simply a scatter plot of the vanadium and the titanium concentrations. And this would be then taking from these the average composition, the average concentration and the standard deviation. So modeling now synthetic data based on average concentration, standard deviation, and you see it looks quite chaotic, yes. And this would then, considering correlations, considering covariance, working with the covariance matrix, which at the end we decided to continue with this kind of synthetic data. And so we have new training data sets of synthetic data. The cone amphoras categories and are 7,000, the Aegean 23,000, and all the amphora categories that we see in Paphos is 33,000 cases for training. The artificial neural network, which we implemented in TensorFlow, has an input layer with 16 features, the 16 element concentrations, and an output layer, or the different models with output layers with 7 units, 23 units, and 33 units, which are the categories. And then we were using 2 hidden layers. The first hidden layer we tested 256, 128, and 64 units. And then a second hidden layer was 32 units. So for these hidden layers, we used rectified linear unit activation, and for the output layer, the softmax. And as I said, implementation in TensorFlow. And this how it looks like now with accuracy, the precision and recall of the synthetic data. First, we put also the synthetic data, then again in our first models, which we use on the original data already. And we see for the support vector machines, there was a clear improvement of the performance of the models. While for the random forest, it did not work as well. And this would be now the same, the accuracy, precision, recall for the different artificial neural networks that we tested. That's 256, 128, and 64 for the first hidden layer. And then we used normalized data as well as raw data. And this would look like now when we compare the synthetic data categorization of the synthetic data with a new artificial neural network and with a support vector machine. What we see is that we have actually a nice correspondence with a cone amphora data set. Again, little bit disagreement with this A and D, but we also have okay, this is what looks like now for the Paphos data set for all the 33 categories, where we have also some of the Cypriot categories which show clear correspondence with the support vector machines and the artificial neural network. But in some of the categories, we have some kind of disagreement. So we try to understand now what we have. But at the end, we also always have to consider that we can only categorize, or to find the right categorization, if we have a predefined categories in our training data set. To kind of demonstrate this is now when we're looking at specific categories in our test data, in this, for example, in this cone amphora data set. The archaeologists are always interested in stamped amphora handles, and we have some of these stamped amphora handles in our data set, and we start now from amphora handles which we actually collected at this site in South Central Course. We see it's all Course A, clear with all the models, and this looks clear. Then we looked, we took some measurements here in Athens at the National Museum of Hellenistic amphora handles. Here it does not look as clear, but you see there's a clear trend to this 2, which is actually this amphora category Course C, which we know. And then this would be now the Roman amphora handles, which we measured this year. And in 2 cases, we have clear identification of the Course A category, of the Course B category. And then in one case, it looks like actually like a Rhodian pattern, where we are not sure if it's really Rhodes or if the Rhodian Perea on Knidos. And these 2 measurements, so these are multiple measurements of the same handle. These are not as clear. This might be at the end Tassos, and this might be then again Course D, where we have this category 20, which is actually a more general Aegean category. The same we tried for some samples, specific samples in this Paphos data set, where we see nicely the prediction of the stamped amphora handles from Tassos, but this is because these amphora handles were actually also in the training data set. And
I know the time has been exceeded.
Okay, so what I want to say is just to say, in this case, we could identify categories, but looking now, for example, at Sinopian amphora, stamped amphora handles, we don't have Sinopian amphoras at the moment in the training data set, so we cannot identify. The future scope is we have a portable XRF measurement, take the portable XRF measurement, we put it in our machine learning model, which might be a trained neural network or the support vector machine, and we get some kind of automated provenancing, some kind of expert system. So this is actually the scope, what we are thinking about, using one single portable XRF. The perspectives is, in our case, we were looking at elemental composition, of course, and machine learning allows for automated and objective categorization. We can also look at other criteria. We can also combine the criteria. And the different attributes can be linked. And then we can link it also as, for example, at attributes like concerning the performance. And in order to train our models, we need large databases, big data. And for this, when I speak to archaeologists, we need a change in the data management practices in archaeological science, according to the FAIR data principles. Sorry for extending my time. Thank you for your attention.
Thank you. Thank you for your illuminating, really and innovative approach. The machine learning and AI is every day continuously grown, in every field of science and art, and of course in archaeometry. And I can see a bright future, fast-growing AI and deep learning applications to archaeomaterials. So let us go straight to the questions. Michaela, you can ask if you like, if there is any question for the first speaker, and then
Yes,
or get
please.
whatever other first or second, because they are similar somehow, machine learning and applications. So any questions, please?
Please don't be shy to ask. They both don't bite. All right, so I have, as always, some confused questions, because Lee, I kind of got stuck at the definition of structured and unstructured data if we talk about getting stuff into a spreadsheet. But then you used spectra to define your wood species, but we can't represent spectra in a spreadsheet. So they're kind of, how does the spreadsheet data need to look like? So we accept it as structured data.
Yeah, no, when I was doing my presentation, I realized I should have switched the cuneiform with the wood species ID, because in the cuneiform, I actually use the name of the element, which is adding in the words, which is why I use a neural network there. For the wood network, what we found was that the XGBoost would stall out a little bit in our testing, whereas, so though it could fit in a spreadsheet, the uniformity of the data seemed to like distract one approach, whereas the neural network was able to cut right through that. And I think that Anno saw something a little bit similar, where like he used a very simple interconnected neural network with the spreadsheet results, and that outperformed the simple linear, which if you follow my paradigm would be sort of a violation, because he's using the chemical readouts from the soil node. So I think that, like, I kind of use that as a guiding starting point for how to choose, but I do think you should always try something else if the first approach doesn't work. But if you ask anyone working in AI, the starting point will be, are you working with structured or unstructured data? Because if your data is structured, these other techniques are much less computationally expensive and run much more quickly. So I think, and I think I'd be interested in knowing the specs on Anno's system, but the neural networks, because they're so much more complicated, are much more computationally expensive, and you could be looking at hours or days with a standard work computer. Whereas with something like gradient boosting or random forest, you're talking about minutes, hours at most, depending on how you set it up.
Okay. If I want to combine my spectra data with archaeological information, like you had with the cuneiform tablets, where do they come from? What is written on them? We have words and everything. There, it would count as unstructured because we have different kinds of information we're putting in that are not all numbers or categories.
Exactly. So if you were adding the text to what's written on it with, say, the chemical readout, there's no way that text is going to fit in a spreadsheet, right? It's something we can reject from the start. Your only option would be neural networks at that point, which again comes with computational cost. And again, some people, like if you bought a video gaming laptop, or someone who has one, if that has either an AMD or an NVIDIA GPU, you're in luck. There are cloud frameworks to run on those, whether it's TensorFlow, which Anno used, PyTorch, which I use, whichever framework. And the way to think about that is, when you have a computer, you have a graphics processing unit, and you have a CPU. The CPU you can think of as a semi-truck, and you're trying to get it from one end of the European Union to the other. And if everything fits in the semi-truck in the right way, the CPU is the best path. The GPU is like having 1,000 convertibles that can race along the Autobahn independently of each other and adapt to all the different obstacles. And that's why unstructured works better, because each one can fit a different box, can tilt it on its side. You're much more flexible with your data presentation, but it's more expensive. You need a lot more fuel for 1,000 race cars than you do for one big semi, compared to how much data is being shipped. So that's why the unstructured approach basically precludes you need the graphic support.
All right. Thank you. Has anyone else a question? Otherwise, I just gonna keep going, so.
I do have a question for Anno, actually. In your results, it looked like a 3-kernel polynomial SVM outperformed 4 and 5. So it's interesting that something that was less complex had better metrics, not overall. There are a couple examples, I think, on some of the other amphora or some of the more unknown amphora where it didn't work as well. But there it was, as far as the SVMs go, is there a reason you think, like, are there specific elements in those amphora that you think would be lending themselves to a less complicated model versus a more complicated model?
This is a good question, yes. These are actually the points, the issues that we are looking at the moment, yes. Okay, everybody knows the machine learning gives you results, but you have to understand, or it does not always give you the right criteria for the categorization. And I know, for example, because we have a lot of amphoras from COS, there we have high actinides, uranium, thorium. On the other hand, we have amphoras from Rhodes where we have high chromium and nickel concentration because it's orphiolitic. So yes, there are specific elements, and we have to see maybe also to put some categories in or take some categories out to play a little bit with the data. Yes, okay. To interpret geology.
Thank you. Anyone else? Then I have a question. Oh, yeah, go for it. Sorry.
I do have a couple questions. They will probably be easy for you very intelligent people to answer, but that's okay. My first one is for Lee. When you were using the spectra within the wood test, like, were you just giving it like the energy and the counts, and then it was just using the first section of the spectra to be able to identify it? And do you think probably that's related to the fact that maybe what's varying more in the wood are those lighter elements?
Yeah, that was my first thought, but like it's really like everything less than silicon. So the only two elements we'd see with reliability would be aluminum and magnesium. So the way we measured it was a colleague of mine, Kevin DeWitt, set up a scanner where we could plug in the tracer XRF and it would sequentially sample in a grid automatically. So we would just place everything, hit go, and then it would take 360 measurements on a piece of wood, slide in the next one. And so with that, like it was analyzing through there. My suspicion, and I'm not 100% sure about this, is that the wood was about this thick, and anything above 6 or 7 keV might penetrate all the way through the wood sample. So it might be that the scatter profile started reflecting the table underneath, because it's really hard to get infinitely thick for wood because it's wood, it's much less dense than a silicate. And so my suspicion is that stretch of the spectrum is entirely from the wood. It's more faithfully recording the sample than anything it might be resting on. And so I think it's less elemental and more density based. that each of these woods has a slightly different cellulose density, and that part of the spectrum is measured so shallowly that's conveying the density information. And I suspect, using that LOI example with the gradient boosting, if I had the density, I could build a density calibration for wood, and what we're really seeing is that different species fall along that, but that's speculation on my part.
Awesome. Thank you.
You can go on
You wanna
if
go
you
and
have
then after-
more.
Oh, okay. I did also have one for Anno, and again, this might be not a fantastic question, but I was wondering if you saw, you mentioned that you used both like raw data and then also normalized data, and I was wondering if you saw a significant difference between how your sort of modeling was performing with the two different types.
I did not really see a clear difference, or it's something what I still try to look at or to evaluate. But at the moment, I don't see clear difference, which is interesting because in these conventional statistical approaches, which I showed before, where we have to do normalization, we have to work with standardization, and it's always a question how to normalize, how to standardize. But for this, with a random forest where we can use non-normalized data, so the raw data, and also with the neural networks, it is, for me, actually, it's interesting. And I started only with normalized data, but then I tried the raw data and it worked. And so maybe at the end, there's something to prefer because the normalization gain gives some kind of maybe bias.
Thank you.
It's interesting, as it shouldn't actually change the structure of the data, right? Because if we're not going for concentrations, but for relations inside of a data set, it shouldn't really matter if we normalize or not, as long as we do the same thing to all the data, shouldn't it? So seeing no difference would make sense if we're looking for structure and relations.
But the normalization is it's one other process in between, and so it's I would actually prefer to work with raw data, and this was something what I found interesting in the models. That's work with the models with the raw data did not show any disadvantage with the normalized data.
Yeah. Which is a good thing. The less we temper with the stuff, as we learned just recently, the better it is. Which also kind of brings me to that question of big data. Because getting really big data would mean that we all need to find rules to collect stuff in the same way, and still we would have differences with different devices. So we would need to have approaches before we can use big data, how to get all the devices to speak the same language. Otherwise, even with raw data, it can't be compared directly. If we're still there, that we need to try to figure out how to get devices speak the same language.
Yep.
So having...
As Lee demonstrated, even if you have the same instrument or the instrument for the same producer, they have differences. So it's you need also, I think you need also machine learning for the calibrations in this case.
Yeah, but that's why I'm wondering how far we can go with pXRF in regard to big data and how far we can go with AI. are we still kind of limited because just of how the devices are? Because they are individuals, so using data just because it's published still is dangerous and might always be. So just something I'm wondering if it's stuff we need to be more aware now that we have all the AI stuff out there and it's much more accessible than it was, that we don't run into the issue creating publications and interpretations based on insufficient data for those approaches, just by throwing stuff together, if that makes sense? Or was it just rumbling?
I think for each individual portable device, we should fight to apply a special calibration procedure which will be compatible to all the other results produced by other devices. There should be something that can be converted from one device to a normalized one for all the devices in the world. I don't know how we can do it, but this is the only way to reply to your question.
I agree with you, Ioannis. I think you know, with the IRN sample that we looked at with that ceramic test kit where we had Niton, Vanta, Brooker, you know, all these SciAps,
Hitachi.
and then Hitachi, that's right.
Don't
We
forget
got
the
them
Hitachi.
for the main series of elements. We saw performance differences for each element, but we could get them to all agree. I think in a perfect world, which does not exist, but in a perfect world, you would have like a recalibration to an agreed upon set like that for everyone participating in, say, Mediterranean ceramic studies. And then that way, Anno's data could be matched with so-and-so's data into a larger network because the outputs would be fixed, right? That's the key goal of calibration. The problem we run into with portable and with laboratory instruments, that is the case, right? Like no one wonders this about like the Fitch's WD-XRF versus, you know, say one in Brooklyn. They're going to give the same results. They do it because they form a fused glass bead, which is a uniform matrix, and then they've got a uniform output from that point forward. With portable XRF, everyone, the manufacturers are competing with each other, trying to get better geometries, solve customers' problems better, and then using proprietary algorithms on top of that. That's where you get words like soil. You know, no one talks about, say,
Different.
geology mode for WD-XRF because, well, there's just a fused glass bead, there's a straight line, that's that. It's the proprietary competition points. And we're basically at that point acting as consumers, not as scientists, I worry, when we're too reliant on those methods or outputs. I think the more we can step away from that, extract the spectrum, calibrate to an internal set of standards, I think that resolves all issues, but it introduces lots of logistical hurdles, like who makes sure someone has access to those standards, who makes the standards, who monitors their quality. You'd need some kind of body to take that kind of work on, which would require funding, which would require sort of a community approach that I don't think exists at this point.
Yeah.
Yeah. But with the start of the global network, we might have opportunities to work together to start something like that, start a database, start distributing, start sharing, and start working together really to create those kind of data sets that we need and to raise awareness together for the things we were just discussing.
Yeah. And I think Europe would be the place to start this because, you know, not to speak as too much as an American, but like we're currently being gutted scientifically as we speak. But I would say write a grant with lots of institutions signed on saying we plan on creating 20 samples for these target matrices that represent most of the use of pXRF. And then we're going to fund for 3 years a set of postdocs who are going to, you know, either provide instructions and work with each person, calibrate all units that want to use this. Here's our standardized approach. We're using these open data protocols, this and this, and see if you can institutionalize that using, you know, that kind of an approach. I think that would be the necessary first step. And I would hope that most researchers would be very eager to jump on board with something like that. But I don't know, what that universe might look like. But I think if I were starting from scratch, that would be the way I would approach it.
Thank you so much. If there are no additional questions, I think this would be a very nice high note to end this colloquium. So I just would quickly hand on to Keelie for the next colloquium advertisement.
Yes, so the next colloquium is actually going to be November 26th at the same time. It's also a Wednesday, so from 6 to 8 p.m. Central European time. And it'll be given by, I'm gonna try and pronounce their names correctly. Did you say her last name?
Yes, Abdelgawad.
Who is actually a chemical engineer and also working a lot with pXRF. And so she's going to introduce, I believe introduce some of, the problems with XRF. And then it's going to be, and some of the solutions that she's trying to create in order to manage those problems. And then it'll be handed off to Camille. Oh, thank you so much for pronouncing their last names for me.
No worries.
Who will be kind of showing a case study of the application of the sort of methodologies that they're developing. So please join us for that. That should be good and exciting. And then we will have one more edition as well in the start of December, since we obviously know that the holidays are kind of take up the end of December, even though we normally have our colloquium then. And that'll be given by Kyle Frund and Ellery Franz. Yes, thank you.
I think
Yes.
the link is the same, isn't it? The link.
Yes, and the link will be the same for all three of those. Yes,
so the link is the
Yes.
same, so you can make a note in your diary for these dates. The link is the same, and we look forward to see you at the next two colloquia.
There's just one thing I also want to add. We will have another pXRF conference in Vienna on the 30th of March. The call for paper is out, and you can find it on the pXRF network website. Also, if you're not part of the pXRF global network yet, just drop me a message and we will add you to the mailing list. And so you get all the information on the next colloquia, on upcoming conferences, and all the fun things you can do if you're interested in pXRF.
And I believe the deadline also for the conference, for the abstracts for the conference is November 30th. So you have a month.
Thank you. So thank you guys for hanging out with us. Thank you for your time. Thank you to the presenters. And for those who have early in the morning, have a lovely day. For the others, have a lovely evening and sleep tight. See you next time.
See you next time.
Thank you so much.
Bye, guys.
Bye.